This is part 5 of a series on the support vector machine. In this video, we will look at the nonlinear SVM. The data points distributed like this are difficult to separate linearly. Instead, it makes sense to separate them into a curve like this. Nonlinear SVM can determine this nonlinear decision boundary. This video was produced in Korean and translated into English. My voice is AI-generated text-to-speech. In the last video, we looked at linear hard margin and linear soft margin SVM. In this and the next video, we will look at nonlinear SVM using the kernel function. In this video, we will look at the basic algorithm of nonlinear SVM. And in the next video, we will implement it using cvxopt and scikit-learn. If linear separation is not possible, a nonlinear boundary can be obtained by converting the data into a space where linear separation is possible, then linearly separating the data, and then converting it back to the original space. This is the idea of the nonlinear SVM. We do not actually convert the data into those spaces. Instead, we use a kernel trick to achieve this effect. The example below assumes that we know the function phi that converts the data from a 2D space into a 3D space. In reality, we neither know nor need to know this function phi. In the example below, 4 data points are distributed as follows. Red data points have a class of +1, and blue data points have a class of -1. This data cannot be separated by a single straight line. Instead, they can be separated by this curve. These data points are distributed in a 2-dimensional space. Let's transform these data points into a 3-dimensional space using the function phi. Let's assume that the transformation function phi is a second-order polynomial like this. If we transform the first data point using this function, x1 is 0 and x2 is 1, so we get 0, 0, 1. If we transform the remaining data points, we get the followings. When the converted data is displayed in a 3-dimensional space, it is as follows. In this space, this data can be separated into 2 clusters by a single plane. This means that linear separation is possible in this space, and linear decision boundary can be created. Therefore, in this space, we can just apply the linear soft margin SVM that we looked at earlier. And when the data in this space is transformed back to the original space, the linear decision boundary is transformed into a nonlinear decision boundary. This is the idea underlying the nonlinear SVM. This is a simple example, and actually we don't know the transformation function phi. Here are the sample results of a nonlinear SVM for the data below. The nonlinear decision boundary looks like this, and the positive and negative boundaries look like this. And the data points on the positive and negative boundaries are support vectors. This example is presented in Figure 7.2 in the book Pattern Recognition and Machine Learning by Christopher Bishop. Again, the decision boundary can be created by applying the existing soft margin SVM to a linearly separable space. Just replace x with phi x in the existing soft margin SVM formulas. We can then find the solution to the Lagrange dual function using the transform data phi x instead of the data x in the original space. The Lagrange primal function using phi x instead of x is as follows. And the results of differentiating this function with respect to w and b are as follows. In this function, phi x is unknown. And since we don't know phi x, we can't use this equation to find w. It is not possible to find phi x and w. However, we can find this value using a kernel function, which we will look at later. If you know this value, you can solve this dual function to find the lambdas. And you can find b using the lambdas and support vectors. Then even if you do not know the phi x, you can create the decision function by only knowing the dot product of phi xi and phi xj and b. This method is called the kernel trick. Next, let's create a decision function. The formula for finding w in linear SVM is as follows. Replacing x with phi x gives us the formula for finding w in nonlinear SVM. Here, the lambdas for non-support vectors are 0, so we can write this expression as the sum of these values for the support vectors. Since phi x is unknown, w cannot be found using this formula. Multiply both sides of this equation by phi x to get this equation. If you know this value, you can use this equation to find the value of w phi x. Next, let's find the b using the support vectors and the lambdas. As we saw in the linear SVM, support vectors satisfy this equation. Substituting phi x for x in this equation, we get the following equation. Even in nonlinear SVM, support vectors satisfy this equation. Substituting these values for w phi x gives the following equation. Since we can find this value, we can use this equation to find b. In the linear SVM, b can be obtained using this formula. Similarly, in nonlinear SVM, b can be found using this formula. This part corresponds to wx. And if we calculate the average of these values over all support vectors, this is the b. The decision function is as follows. This part is wx. We can calculate this part for any test data. And since we can find b using the equation above, we can finally calculate y hat. When you enter a test data point into this formula, if y hat is greater than 0, the class of the test data is predicted to be positive 1. If y hat is less than 0, it is predicted to be negative 1. Next, let's look at how to find the dot product of phi xi and xj. Let's first look at the example below. Let's assume that the transformation function phi is like this. The first data point x1, 0, 1 is converted to this point, and the second data point x2, 1, 1 is converted to this point. If we find this value for the first and second data points, we get 1. In this way, we can find the dot product of phi xi and phi xj for these data points. This time, let's calculate the dot product of phi xi and phi xj without knowing phi itself. Instead, let's define a kernel function like this. This is a quadratic polynomial function. If you calculate the square of the dot product of the first and second data points, you get 1. The rest of the data points are calculated in the same way. The results are the same as above. Therefore, you can see that even if you do not know the function phi, you can calculate the dot product of phi xi and phi xj by using an appropriate kernel function. In general, polynomial, Gaussian, sigmoid functions, etc. can be used as kernel functions. This time, we will look at kernel functions. Several kernel functions are known, and these functions can be combined to create new kernel functions. The kernel function is denoted by kx, y, and the basic kernel functions are as follows. A p-order polynomial can be a kernel function. If p is 2, the two-dimensional data point x is transformed to the three-dimensional data point like this. The general form of a p-order polynomial is as follows. If p is 2 and c is 1, a data point x is transformed like this. The two-dimensional data point is transformed to the six-dimensional data point. Gaussian function can also be a kernel function. Here gamma is defined as follows, and the sigma is the standard deviation. Gaussian kernel transforms a data point x into infinite dimensions. And the sigmoid function can also be a kernel function. In the strict sense, the sigmoid cannot be a kernel function. This is because it does not satisfy Mercer's theorem, which we will see on the next page. However, it is said to be widely used as a kernel function. More details on this can be found in this article. In the code on the last page, we will see why sigmoid cannot be a kernel function in the strict sense. It can be easily proven like this that a quadratic polynomial can be a kernel function. We are not interested in finding the phi x itself. We are only interested in finding the dot product of phi xi and phi xj. If k1 and k2 are kernel functions, the functions below that combine them can also be kernel functions. For more detailed information, including proof of this part, please refer to the book below. Next, let's look at the kernel matrix, positive semi-definite, and Mercer's theorem. A matrix generated from a kernel function is called a kernel matrix. This is an example when the number of data points n is 2. The dot product of these two is equal, so the kernel matrix K is symmetric. And the key theorems about symmetric matrix PSD and PD are as follows. PSD stands for positive semi-definite, and PD stands for positive definite. For any real symmetric matrix M, the following theorems hold. For any real vector X, any matrix M that satisfies this condition is positive semi-definite. The kernel matrix K is symmetric and PSD. All eigenvalues of a symmetric matrix M are real numbers. And if all eigenvalues of a symmetric matrix M are non-negative, then M is PSD. Since the kernel matrix K is also a symmetric matrix, if all eigenvalues of K are non-negative, then K is also PSD. Next, let's look at Mercer's theorem. Mercer's theorem helps us check whether a function is a kernel function or not. If this condition is satisfied, the kernel matrix K is positive semi-definite. If K is continuous symmetric positive semi-definite, the following inequality holds. and all eigenvalues of K are non-negative. If the above conditions are met, then K is a valid kernel. Please refer to the book below for further details, including proof of this part. Finally, let's check whether the given kernel function is valid or not. As seen in the definition on the previous page, we check that all eigenvalues of the kernel matrix K are non-negative. For arbitrary real data, if all eigenvalues of the kernel matrix K are non-negative, then K is positive semi-definite, and the given function is a valid kernel function. Generate two-dimensional random data points. Let's check the validity of the four kernel functions below. Generate the kernel matrix K for a given kernel function. Then find the eigenvalues of K. Let's print the maximum and minimum values of the eigenvalues. For RBF or Gaussian function, the minimum eigenvalue is 0. All eigenvalues are non-negative. So RBF can be a kernel function. The same goes for the polynomial. In the case of sigmoid, the minimum eigenvalue is negative 0.0034. This value is negative. Therefore, strictly speaking, the sigmoid function cannot be a kernel function. However, the sigmoid function is also widely used as a kernel function. Please refer to this document for more details. For the cosine function, the eigenvalue is negative 8.62, which is clearly negative. Therefore, the cosine function cannot be a kernel function. Let's run this code. The results are as follows. So far, we have seen how nonlinear SVM works. In the next video, we will implement a nonlinear SVM using CVXOpt and scikit-learn's SVC.